So back when I was thinking about titles for this talk, I was playing around with a few different ideas, and what I eventually settled on was this transactions, myths, surprises, and opportunities, thinking, that had at least a modicum of optimism and opportunity in it. But actually, my working title internally was more something like Transactions, Joys, Challenges, and Misery, with a subtitle of Consistency Guarantees. You want consistency guarantees? Ha, 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 consistency guarantees, consistency guarantees. So you see, looking at this topic has driven me a little bit insane. And so I'm going to try and see whether I can drive all of you insane too, with the forbidden knowledge in this talk anyway. A lot of fairly crazy things. I've got a lot of material, so I'll have to go through it fairly quickly, but hopefully we'll have enough time. So at the moment, I'm writing this book for O'Reilly, and this talk is kind of an extract of one of the chapters of the book. So if you find the kind of stuff interesting, this book tries to kind of lay out a lot of the underlying big ideas and principles that you find in not just databases, but other kind of data storage and processing systems as well. It's not finished yet, but you can find an early release, like a beta release of the first 8 chapters at dataintensive.net. So going back in the history of transactions, I like looking back at the history of things a bit and understanding where things came from. And if you look at the kind of transactions you find in most relational databases nowadays, you can trace them pretty directly back to a system called System R that was developed by IBM in the 1970s. And a lot of the terminology and the ideas we use for talking about transactions really follow on fairly directly from this system 40 years ago. And in history, like, people have been working on databases a long time, but that's basically been the dominant model for a long time. Until then, in the mid-2000s or so, this NoSQL thing became trendy. And then, of course, the inevitable counter-movement of new SQL happened. But if you think about this, it's not really about SQL. Like, people have started building SQL engines on top of HBase and such like, for example. So it's whether or not these systems support SQL is, there's a bit of a data model question there, but otherwise it's kind of not that, it's kind of beside the point, because the biggest difference between these systems is actually whether or not they support transactions. It's more like a movement of no transactions versus yes to transactions. And if we're talking about transactions, we inevitably have to talk about ACID. So you're probably familiar with this acronym. It stands for Atomicity, Consistency, Isolation, and Durability. So you think you know what it means. And what I'm going to show you in the next half hour is that you probably didn't actually know what it means, because, what does something like isolation actually mean if you unpack it in a little bit more detail? So it turns out that actually this acronym is, one polite way to put it is it's more mnemonic than precise, which is how Eric Brewer expressed it, which is basically a way of saying, it doesn't really have a well-defined meaning. It's just kind of a marketing term that we use to very loosely associate systems. So I'm going to try and run through each of the letters briefly and just expand a little bit on what it actually means so that we know what we're actually talking about when we're talking about transactions. I'll start with durability because it's kind of the easiest one. So back in the day, when these earliest transactional systems were being built, durability meant that the transaction log is written to an archive tape, because disks were not that reliable, and at least with a tape, you could then, if the disk crashed, you could then replay the transaction log, the redo log of this archive tape, and thus restore the contents of the database. But then, of course, tapes fell out of fashion, and durability became known as the data is f-synced to disk, so if stuff crashes, then hopefully it's still there. And then more lately, this has kind of been further interpreted and thinking, well, a disk on one machine is quite nice, but if that machine becomes completely inaccessible due to, its CPU failing, and so you might get it back again eventually, but some engineers have to go into the data center. So actually it'd be nicer if we just replicated the data across multiple machines, and thus, if the data becomes unavailable in one place, hopefully it's still available in another. But anyway, this is all just to say durability means that once you've written something, you're hopefully not going to lose it again. You're hopefully going to be able to get it back again when you ask for it. So that's a fairly simple one. What about the C, the consistency? This one is often misunderstood. You might have heard of something called the CAP theorem, which talks about consistency, availability, and partition tolerance. The C in ACID is not the same as the C in CAP. They both stand for consistency, but they have two totally different meanings. I'm not going to go into a lot of detail on CAP. Personally, I don't think CAP is helpful at all. I've written a whole paper about explaining why I think it's not helpful, so you can find that on archive.org if you are so inclined. But just keep this in mind. What consistency means in the context of ACID is that when your transactions which execute on the database will move the database from one consistent state to another, where consistent means it satisfies certain integrity constraints or certain invariants. Like an invariant might be that in an accounting system, all of the account debits and credits sum to the same quantity or something like that. Or it could be a uniqueness constraint that you only have one user for a given username in your database. The weird thing about this consistency is that it's not actually something that the database can guarantee by itself. It's something that the application can guarantee by relying on certain guarantees of the database. But it's this interplay between the application and the database. So it doesn't make sense to say that a database provides consistency in the ACID sense. It's an application using a database that provides consistency. So it's kind of an odd one out in this acronym, and in fact, people who know the evolution of these stories have said that the C was basically tossed in to make the acronym work. It was not considered important by the people who defined it at the time. So C we can more or less ignore. What about A, the atomicity? So if you've done any kind of multi-threaded programming, for example, you've probably come across atomic operations, like an atomic increment or atomic compare and swap operation or something like that. Confusingly, the A in ACID is not referring to this kind of atomicity. So again, we've got an overloading of terms. It's really unfortunate. But in the context of ACID, this atomicity is not about concurrency. It's not about what happens if several things are happening in parallel. It's about fault tolerance. It's what happens if something goes wrong in the system. For example, something crashes. So the typical scenario would be you have two things that need to be updated together because they kind of express the same thing in some sense, or they are closely linked to each other. So like, say you've got some kind of auction website where somebody can buy a product, and then when somebody's bought something, you need to say that the buyer of this item is the person who bought it, and you also need to send an invoice to the person who bought it, or something like that. And now what happens if these are two separate writes, and the first one succeeds and the second one fails because something crashes, or someone unplugs the wrong network cable, or whatever. Something goes wrong, and now you've kind of made half the changes that you wanted to make, and once the system comes back up again, it's going to be in an inconsistent state, unless you have some way of saying these two modifications, these two writes, have to happen as one unit. They're one atomic thing. And so I want them either to both succeed or to fail. And if it fails, I can retry again. And so that's really what transactions provide, is this atomicity across multiple objects. That is, atomicity on a single object, like a single row in a table, a single document in a document database. That's basically simple. So, and any storage engine will provide that. But the key with transactions is that you can kind of wrap a little box around several writes and say, these all belong to one atomic unit. So this is what the A in ACID is talking about. And a key here is that if something goes wrong during the execution and the transaction has to abort for any reason, any partial writes that happened there will be rolled back or undone or discarded in some way. So really, a better word than atomicity would have perhaps been abortability, because the important thing that makes these transactions work is the fact that they can be aborted, and if they are aborted, then it's as if nothing happened. Now, aborts are super helpful because they collapse a whole range of different error classes into a single thing that you can handle. So it doesn't matter whether the transaction is abort is because the application server crashed, or because the database server crashed, or because somebody unplugged a power cable, or someone unplugged a network cable, or the switch crashed, or something else went wrong in the network, or you got a deadlock between different transactions, or some integrity constraint was violated. All of these things just get collapsed down to a single thing, which is the transaction aborts. So the whole point of this transaction atomicity is really a feature to make life easier for application developers. And that is, you don't have to worry about handling all of these different error scenarios in the application because they've been collapsed down to a single thing. And the response, if a transaction aborts, is, well, you can just safely retry it. OK, so much about atomicity. We said that that's about fault tolerance, but there is still the concurrency issue. And I skipped over the I earlier. The I, the isolation, that's where we're talking about concurrency. And this is where it starts getting really interesting. So if you look at a database textbook talking about ACID, it will say that isolation means serializability. And the idea of serializability is that each transaction can pretend that it has the entire database to itself, that there's no other concurrently executing transactions on the database. Or put another way, the result of executing all of the transactions is the same as if they had executed one after another without any concurrency in a serial order, hence the name, serializability. Now, if you actually look at what databases do in practice, we've got some support serializability, but there are also these various odd other, what I call isolation levels. There's things like read committed and repeatable read, for example. And these things are a little bit hard to understand. I'm just curious, is there anyone here who thinks they can explain off the top of their head what's the difference between read committed and repeatable read? No, one person. So the challenge with these things is this is a configurable property of your database transactions. And if you've written an application that relies on transactions, you have to understand what guarantees you can rely on from the database and which you can't. So if you don't understand the difference between these isolation levels, how on earth are you supposed to write applications that are correct and that don't have race conditions? I'm going to show a few examples of how these things can actually be quite subtle. And so in practice, what happens is that these various databases have various different isolation levels, and the default is often quite weak. So read committed is the default in about half of the different database that was surveyed here. And like a whole bunch of these databases don't even support serializable isolation. So you're forever stuck at some of the weak levels. This is a very nice survey by Peter Bayliss and some of his collaborators, which you can look at and be depressed if you want. Anyway, so I'd like to give a bit of a flavor of what the differences between these isolation levels are, because I think it's actually quite interesting, and it's good to understand this stuff. So I'll start with read committed, which sounds like, that's what we want of a transaction. We only want to read committed data. That sounds like a reasonable thing. And the way read committed is defined is that there are two anomalies that are not allowed to happen. So an anomaly in database speak is like a race condition. It's some kind of weird behavior that would not be possible under a serial execution. So something where kind of this idea that each transaction has the entire database to itself, where that idea becomes violated. And these two things that read committed prevents are dirty reads and dirty writes. So dirty reads is what read committed says in the name. That is, a dirty read would be reading some data that has not yet been committed. So you read some transaction writes some data, but it's not yet been committed, and another transaction reads it. So preventing dirty reads means you only ever read committed data. And that sounds quite reasonable, OK. And dirty writes maybe needs a diagram to explain, so let's have a diagram. So imagine you've got two clients, A and B, and they are writing to the same database, and there are two objects, like two rows or two documents or something in that database. And A wants to set both objects to A, and B wants to set both objects to B. And they do this concurrently. And so if you look at X, that first gets set to A by A, and then gets set to B, and the final value is B. Whereas if you look at the object Y, it actually gets the ordering the other way around. So it first gets set to B, then gets set to A, and the final value is A. And now your two things have gone inconsistent. So, you know, this, in the auction website example, you could end up with an invoice being sent to one user and the buyer being actually set to the other user. And so those people will not be particularly happy. But read committed prevents this from happening. And so that's already good news. So most databases that have some kind of concept of transactions will prevent this dirty writes. And typically the way they do it is that it just take a lock. So in this case, the first transaction writing to a certain item will take a lock and keep that lock until the transaction commits or aborts. Okay, so I think you'd be forgiven for thinking that if you're preventing dirty writes and dirty reads, you know, that's kind of, and you've got atomicity, that's kind of what transactions are, right? So what are all of these other weird isolation levels here? What I'm going to try and show is some examples of race conditions or anomalies that can occur at read committed that are prevented at some of the stronger isolation levels, and they're not quite as obvious. So take this one, read skew here. This read skew differentiates between read committed and repeatable read or snapshot isolation. And so this is a problem that can occur under read committed. So the scenario is this: say you've got a bank and a user wants to transfer £100 from account X to account Y. And so what they have to do for that is to decrement account X by £100 and increment account Y by £100. And so the sum of all of the accounts stays the same. They've just moved money around. And now this is all fine. But now imagine what happens if concurrently you have some kind of process which just reads the entire database. And maybe that's like a backup process that is just taking a copy, or maybe it's some kind of analytics process, or like periodic checking integrity of the database. And this is going to first read the account Y, and it's going to get back 500. And then it's going to read the account X, and it gets 400, because by the time it gets around to reading X, that transaction which transfers the money has already committed. So this is read committed. The change has been committed by the time X is read. But you've got this weird inconsistency where, you know, you're supposed to have a sum of £1,000 in both accounts in total, but actually this orange process sees a sum of £900. So it seems like £100 have just evaporated from the point of view of this orange process. So that's kind of bad news. And this is what repeatable read and snapshot isolation were invented to prevent. And so these are kind of the most confusing isolation levels because the naming gets very inconsistent depending on which database you look at. So the traditional implementation of repeatable read in System R style, 1975, you can still find in SQL Server nowadays, for example. So if you use repeatable read in SQL Server, you get basically the same as what System R did back then. But most databases actually do snapshot isolation rather than this taking locks. The idea with this is that each transaction gets a kind of consistent snapshot that it can read from. And for that, it doesn't need to take a copy of the entire database. It uses some clever multi-versioning on the individual rows in the database. But logically, it seems to the transaction as though it's executing at one point in time. So even if subsequently that data gets changed by other transactions, any long-running read-only transaction will only see the data at some point in time. And so like Postgres called this repeatable read. MySQL does it almost right, but not quite. Oracle actually calls this serializable, just to be confusing. SQL Server calls this snapshot. Anyway, so it gets kind of inconsistent, but the high-level principle remains fairly similar across these different databases. Okay, but we're still not at the top yet. We're still not yet at serializable. So what is the difference between something like repeatable read and snapshot isolation and higher up serializable? So here's another example. This example is called write skew. And the scenario is as follows. Imagine this is a dispatch service for ambulances, and you want to make sure that you have at least one doctor on call always, all the time. And so doctors can trade their shifts, like it could be that at some point a doctor is not feeling well themselves, and so they want to ask one of their colleagues to take over. And that's all right. The invariant you want to preserve here is that at all times, at least one doctor is on call. And so this is the transaction that gets executed when a doctor clicks on the web interface saying, hey, I'm not feeling well, can someone else take my shift, please? A transaction is as follows. It first counts how many doctors are currently on call. And if that number is greater or equal to 2, then it's OK for the current doctor, like currently Doctor 123, to go off call. So it then updates the doctors table. And this seems like it should be safe, because in a serial execution of these things, you would make sure that one transaction executes decrementing the number of doctors to, say, 1, and then if a second doctor also tries to further decrement it to 0, they won't be allowed to do so, because it's realizing, oh, there's only one doctor, you're the last doctor on call, so you're not allowed to go off call. You have to negotiate it some other way. But in something like repeatable read or snapshot isolation, this actually turns out not to be safe. So you could have a scenario like the following, where, OK, you've got 3 doctors, Alice, Bob, and Carol, and currently Alice and Bob are on call. And Alice and Bob are both currently feeling unwell. So Alice goes into the system and says, hey, can I go off call, please? And the system says, yes, sure. There are currently 2 doctors on call, so it's safe for you to go off call. And then concurrently, Bob does the same thing. And Bob also sees there are 2 doctors currently on call, so it's safe for you to go off call. So each of these individually updates their own row in the database. And note that these are 2 different rows, so they don't conflict with each other. There's no lock or something like that to prevent this. And now, well, both transactions successfully execute and commit, and now you've got no doctors on call. And so this is exactly the situation that we wanted to prevent. So the pattern here is called write skew, and there are several different ways how it can occur, but kind of one way of thinking about it is the following pattern, that you've got a transaction which first reads some data and then makes a decision based on the result of what it has read, like, for example, are there enough doctors on call? And then it writes something to the database as a result of that decision. And different transactions might write their result to different places in the database, so those writes are not going to conflict with each other. But the write may change the thing that was initially read. And so it could happen that by the time the transaction commits, the thing that it originally read, which is the premise of the decision that it made, that thing that it originally read may no longer be up to date. And this is the problem of write skew. So it could be that the decision was made on a false premise, basically. And serializable transactions are supposed to prevent that. Which then leads us to the problem of, well, if all of these issues, these race conditions can occur, why doesn't everybody just use serializable transactions? And the problem is that they're kind of expensive, or at least historically they've been kind of expensive. Because, well, since System R came up with serializable transactions, the one way of implementing them has been two-phase locking. So this algorithm says that basically whenever you read or write anything, you have to take a lock on it, and you have to keep that lock until your transaction commits or aborts. And so this is a fairly pessimistic concurrency control scheme. In this doctor's example, what it would mean is, say you've got this query which looks at all of the doctors' on-call status. You would now have to take a shared lock on all of these doctors that you've read. So you could imagine in a large query, this is potentially taking a shared lock on the entire database, effectively. And the shared lock means that other transactions can still keep reading that data, that's all right, but nobody can write it, nobody can modify that data. So essentially what you're doing with two-phase locking is you are blocking the entire database for writes whenever you're making any large read. And, well, this has kind of bad performance implications. And if you've got even just like a single person running a backup query or some analytics query, it's not very kind to stop writing or stop all writes to the database for a long time. And that was really the motivation of introducing all of these weak isolation levels, like read committed and so on, in the first place. It's because these locks were simply too expensive, and people wanted a get out. And in fact, the definition of these isolation levels was actually, well, the System R team back in 1975 or so, they just decided to not hold the locks for so long. They just decided, okay, we're going to change our long locks to short locks that are only held for a brief moment and then released again. That is why those different isolation levels are so hard to understand. It's because they're not defined in any sort of sensible semantics that is designed for humans to understand. They're defined in terms of the implementation details of a 1970s database. That's why. So fortunately, things don't stand still. Well, they kind of stood still for about 30 years, well, 40 years even, but eventually people did figure out better ways of implementing serializable transactions. And kind of two different approaches came along at almost the same time. One is implemented in an academic prototype called HStore, which is commercially now known as VaultDB. A different one is called serializable snapshot isolation, which is implemented in Postgres and FoundationDB, for example. So I'll run through each of those briefly. This is first of all, the HStore approach, which is actually remarkably simple. And really, people should have been doing this stuff earlier. And that is, if you want your transactions to be serializable, well, just literally execute them in a serial order. And if they are literally executed one after another, then no concurrency exists. Like, you've trivially single-threaded the entire problem. And as long as you can make your transactions fast enough, it's actually quite viable to take all of those concurrently executing stuff and just stick them one after another. However, there are a few practical things if you want to make this work. This is only going to be feasible if each transaction individually is super, super fast to execute, because otherwise your throughput is just going to be abysmal. So in order to make every transaction as fast to execute, you have to kind of change the model a bit. One thing that you need to do pretty much is to keep everything in memory, because going to disk and waiting for disk to come back while you've got a queue of other transactions waiting to execute serially, that's just going to be too slow. You can do things like aborting a transaction if it has to read from disk and then restart it again once the data has been loaded into memory, things like that you can do. And you also need to run everything as stored procedures, pretty much. So there's no way you're going to wait for a network hop back and forth in some EC2 crappy data center for several milliseconds while this transaction is executing. Again, that would just drive your throughput down to 0. So you need to be able to simply enqueue a transaction and say, do that for me, please. And the database has to be able to execute that entire transaction from beginning to end very quickly. And you have to partition the workload so that you can actually make use of more than one CPU core and more than one machine, and so on. But this is a reasonably viable way of building systems. So that's one way of achieving serializability. The other way is to detect conflicts and abort transactions if necessary if conflicts occur, which is kind of the optimistic counterpart to the pessimistic approach of two-phase locking. So this number 3 approach is known as serializable snapshot isolation. And so the idea only came up in 2008 or so. But actually, the implementation looks kind of similar to two-phase locking. You've also got these locks that you take, but with one crucial difference is that the locks don't block anybody. They just gather information. So that is in this case where you're querying the on-call state of all of the doctors. You're, in some sense, taking a lock on all of the doctors, but that block doesn't prevent anyone from writing and from updating those doctors. It only helps the transaction gather the information that, oh, there's somebody who read this data about which doctors are on call, and somebody else has modified this data that who is on call. And so you can now collect these bits of information about which transaction has read and written what, and then when a transaction comes to commit, you can do an analysis on this graph of different reads and writes and figure out whether any conflicts have occurred. And there's some really clever algorithms which, if you're interested in this stuff, I encourage you to look at. The papers are quite readable. Anyway, if there's no conflict, then the transaction is allowed to commit. So this is basically the overview of new ways of implementing serializability. And I think they're quite interesting. So Postgres does this kind of thing on a single node. And so Postgres' serializable transactions actually have rather good performance. The only distributed implementation that I'm aware of has been in FoundationDB, but they unfortunately got bought by Apple, and now the product isn't available anymore, which is a great shame. So if someone wants to implement SSI in a distributed way, I think that would be an interesting thing to do. So that's been our overview of these various different isolation levels. But most of what I've talked about has been in the context of a single database, like a single application running on a single database. But modern systems are unfortunately more complex than that. So with modern systems, you often have various different services which maybe each have their own database. You might be wanting to use several different databases across several different services. People use buzzwords like microservices. I've been working on stream processing systems which have many similar characteristics where you're trying to kind of break a large, big monolithic thing down into more manageable chunks. And part of this breaking down is that you've now got data sitting across different databases. So on a high level, these systems tend to look something like this. You've got some kind of service which has some code in it and probably got its database co-located with that service. And if one service wants to communicate with another, it's going to make some kind of RPC calls or some kind of REST requests to other services. And if you draw the same diagram for stream processing, it looks basically the same, except the arrows are streams of events rather than RPC calls and REST. But a key idea here is that in this kind of architecture, you kind of draw a box around each of these services and say, OK, we may have transactions within one of these services, but we're not going to even try to have transactions across different services. So we kind of put a boundary around this. So I was kind of intrigued by this and thought, well, you know, would it be possible? Would it even make sense? Would it be sensible to have some kind of transaction concept across multiple services? Of course, I wasn't the first to think of this. People have been thinking about this for a long time. In fact, atomic commit protocols do this kind of distributed transactions. So two-phase commit is probably the most well-known. Sorry, the naming is really confusing. This is two-phase commit. Earlier I was talking about two-phase locking. The names are very similar, but they're two completely different things. But anyway, so this is the idea that you can have some kind of transaction manager which coordinates across multiple services and multiple databases whether a transaction gets committed or aborted. And people have built these things, but you know, they're actually not particularly reliable, and the performance is pretty terrible. And so, you know, this doesn't seem particularly great. Interestingly, there's a strong connection here to the problem of totally ordering things. So I said, with serializable execution, you want the system to behave the same as if things happened one after another in a total order. Well, you can put things in a total order. And there are systems which will, in a distributed system, put events in a total order, but they are equivalent to consensus systems. So Zookeeper, for example, provides a total ordering of events, and it does that through a consensus algorithm. All of these three things are expensive. And that means every time you want to write something, you've got some kind of coordination happening over the network. Sometimes the fault tolerance of these things is not great. And what's more, they have a real failure amplification problem, and that is, if you want to transactionally update data in several different services, and one of those services is going bad for some reason, like it's running slow, or it's currently offline, or you deployed a buggy version of that service, or whatever, if you're trying to atomically commit across multiple different services, that one faulty service is going to bring down the entire rest of the system, which is exactly what you wanted to avoid in the context of splitting things across multiple services. You wanted to isolate the failures. You wanted them to not spread across the entire system. So if you introduce some kind of distributed transactions here, it seems like you inevitably bring back that failure amplification. And it gets even worse if you've got your systems geographically distributed around the world, because now in order to do any kind of atomic transaction commit, they're going to have to synchronously coordinate over these really slow wide area links. So, you know, basically it seems like distributed transactions are not going to work particularly well. But, well, what kind of situation do we end up in then? What do we do instead? And I've looked at various things that people have said about building microservices, and I've talked to various people building these things, and I've been involved in building some of them myself. And the general idea I seem to get is, well, you know, if you can't guarantee any sort of atomic commit across multiple services, you have to do things like compensating transactions. And that is, you run a transaction, you do a thing, and then if later it turns out that actually some other part of the system failed, then you run another transaction there saying, actually, can you undo whatever it was, whatever the effects were of that initial transaction, which is somewhat like the abort, the rollback that you get with kind of traditional transaction atomicity, except that you're implementing it yourself in application code. And that's certainly one way of doing things, and you know, maybe that's really what we have to do, but there are still tricky parts about that, like how do you figure out exactly what you need to undo, and what has happened if some other people have made subsequent decisions based on the state that you've now rolled back, and so on. You have to think about it very hard as an application developer. And another thing that I've seen suggested is that, well, if you can't guarantee integrity constraints and consistency guarantees, like maybe you simply need to introduce apologies. That is, for example, you've got an online store and you accidentally sell more items than you have in stock. And you know, what do you do in that case? Well, somebody's simply not going to get the product that they ordered, so you send them an email saying, hey, sorry, we thought it was in stock, but actually it's out of stock. We'll refund it for you and maybe give you a voucher for £5 off your next order or something. And businesses do this all the time. But if you think about it, what this apology is basically a way of recovering from violating some integrity constraint. So your integrity constraint was you don't sell more items than you have in the warehouse, but if you accidentally do, well, you can apologize afterwards. Now, thinking about this, the compensating transactions, that looks a bit like atomicity, like the A in ACID. And those apologies, they kind of look like the C in ACID in that they're a way of enforcing invariance about your data after the fact, admittedly, but still they're a way of getting some kind of consistency back in your database. Which leads me to an assertion. You see you've got here A and C, and you could imagine some kind of isolation and durability coming up here as well. This leads me to assert that every sufficiently large deployment of microservices contains an ad hoc, informally specified bug-ridden, slow implementation of half of transactions. Apologies for this. I have no evidence to actually back this up, but I'm just going to boldly assert this. But there's still problems here, and that is, we saw with our discussion of the different weak isolation levels that weird things can happen. Like you can end up with having 0 doctors on call, even though you thought you had more than that on call. And so I'll run through one final example of issues that can happen in a kind of microservices world, where maybe we want some kind of transaction isolation. And that is, imagine you have some kind of social network-like thing, and scenario is that one of your users broke up with their significant other, with their boyfriend or girlfriend, and so they unfriend their ex on your service, and then they write a nasty post to all of their remaining friends saying how nasty this person is. And the intention of the user is, of course, that the unfriend happened first, and thus this nasty message doesn't get sent to their ex. But in a microservices environment, you've probably got like the friends service handling the unfriend request, and you've got some kind of post service handling the fact that some update was posted. And now what if you have a third service that is some kind of notification service that sends out push notifications or emails or something like that based on events that are happening in the system? So you could end up in a situation where the unfriend event is delayed somewhere in the system. Like maybe it's just a slow network or something. It can very easily happen. And so the post to friends gets there first, and it scatters email notifications and push notifications to all of the friends, and only then it gets the unfriend event. And then it goes, oh, oops. I shouldn't have sent a notification to that user. Kind of too late now. So what we've got here is a causal dependency in the events coming into the system. That is, from the user's point of view, the they expect the effect of the unfriend event to take the unfriend event to take effect first, and then the message posting to take place. But this ordering dependency has not been captured in the rest of the system, and somehow that has been lost, and that leads to violating the user's expectations. So this leads to some interesting area of research happening right now. And that is, there are things in between the kind of eventual consistency, no guarantees whatsoever, and the very strong serializable, we're going to do everything very strictly in order guarantees. And that is, there are models of causal consistency, for example, which try to capture these kind of dependencies, like that the unfriend should happen before the message posting. And the interesting thing is that causality can actually be implemented without this global coordination. So it doesn't require you to go back to the world of two-phase commit and consensus on every single write. But there are still overheads to it. So you have to track a certain amount of metadata, and there are like open research questions around how efficiently it can be done. But causality, I think, is going to be a very interesting area to explore here in future, because if you think about what a consistent snapshot means in a database, for example, in snapshot isolation, well, that consistent means that it's consistent with causality. That is, you don't end up with some state of the universe where things that happened later appear to happen earlier, and things get kind of reordered in weird ways. So causality is really the key to understanding this. And so in this whole world of different isolation levels, there's actually a reasonable amount of isolation that can be implemented without consensus and two-phase commit and distributed transactions. And the border is somewhere roughly here. So there's a kind of isolation level that's just slightly weaker than snapshot isolation, which can include causality and which can be implemented without coordination. So far, only academic prototypes of this stuff exist. I do hope that these ideas make it out into practice, because I think they're really going to help build applications that are better, more reliable, that don't have weird bugs. If you're interested more in this stuff, there's a whole long list of reading. This is page 1 of my excessively long references list, which extends for page 2 and page 3, and page 4 as well. But you know, everyone says read papers, and here's some, these are all excellent papers, which are all worth reading. So that's, if you want to deep dive into this stuff, there are loads of excellent ideas in these things. If you want a kind of pre-digested version of it, I will actually be giving out free copies of my book. So O'Reilly has kindly printed off a couple of copies of this for me to give away. So even though it's not finished yet, this is like the first 8 chapters in printed form with a big thing on the front saying it's not finished yet. So at 12:30, back at just right out there, I'll be giving away signed copies if you're interested, or otherwise there's a discount code as well. But yes, this has dragged on for a fair amount of time, but hopefully there have been some interesting ideas in there. Maybe I have a little bit of time for questions as well.
Yes.
We do? Great.
Okay. So thank you, Martin. That was fantastic.
Thank you.
Yes, questions, okay.
The issues that you mentioned for the microservices, the ad hoc implementation of transactions, do they apply to replicated databases as well?
Yes, there's a close link there. So a lot of the problems that you would need to solve in having transactions across multiple services would be the same as a replicated database has to solve internally. The main difference there being that if it's a single database, then the developers of that database can implement the algorithms within the kind of little closed walled garden, in a sense, of that one database. So they can do more interesting things. Whereas if you want to have real distributed transactions across different services, you have to kind of agree on some kind of standard. And so like two-phase commit is basically the lowest common denominator that people have managed to agree on, even though it's actually a pretty bad algorithm. But anything more powerful than that has just proved unfeasible for different vendors to actually agree on.
Okay, thank you.
Thank you. Any more questions? Yes?
Sorry. How do you think we ended up with this mess, with this entire confusion with naming and every vendor making whatever they want of those terms and those definitions?
A few different effects, I think. So one thing that I find really strange, but seems to be true, is that on the academic side, the database community and the distributed systems community have historically been entirely separate and basically not talked to each other, which means they've each evolved their own kind of jargon with the same word meaning different things in these different fields. And nowadays that seems bizarre because almost any interesting database is distributed, but like for decades, they've evolved separately. I think we actually wouldn't have many of the problems now had they simply talked to each other more in the 80s. But anyway, hindsight is such. Another effect is kind of well-meaning standards. So like the SQL standard, for example, prescribe these different isolation levels, like read committed, repeatable read, and so on, and try to describe them kind of in sort of general terms that would not be tied to any particular implementation. Unfortunately, they actually failed at that goal of describing them in a neutral way. And so as a way, then, like, for example, Postgres wanted to implement repeatable read-like things, but they wanted to actually use snapshot isolation because it performs much better than locking repeatable read. But they called it repeatable read anyway because that's what the SQL standard says. And it looks kind of similar enough that it just about satisfies the standard. And so even though it's terribly confusing, you kind of ended up there where the same word means different things in different contexts. So a lot of it is kind of historical accident, and hopefully we'll be able to dig ourselves out of that hole eventually.
Create a new standard.
Pardon?
Create a new standard.
Yes, exactly. There are 20 competing standards. Let's create a new one.
Any more? Yes.
Hi. So certain databases have introduced the concept of time with every table or whatever. I'm thinking of Rich Hickey's database. Can't think of it. Yes. Does that have any effect on transactions, or is it purely a nice to have for time traveling and replayability and stuff like that?
There's a bit of a connection there. To some extent, it's an application level feature, so you can do queries of a past snapshot of the database, which is a useful feature to have in some circumstances. There's a cost associated to it because like your garbage collection of old data is more constrained. So the link there I see is kind of to snapshot isolation. So with snapshot isolation, you've kind of implicitly got a timestamp at which you're querying the entire database, though that timestamp is not normally exposed to applications explicitly, and you can't ask for a transaction at some past point in time unless that has been kind of marked as like an, I forget what, some databases have this concept that one transaction can join another transaction snapshot. So there, that kind of starts going in that direction. So I think there's some overlap, but it's not exactly the same thing as well.
So I can imagine that for the serializable model, there are some theoretical tools to argue about situations. But are there, or at least is there hope to have like some sort of theoretical tools like logic or I don't know, whatever, to argue about the other kinds of transactional models? About
the weaker transaction isolation models? Yes, so there's some theoretical work, surprisingly little actually. I guess the main reference there would be Atul Adya's PhD thesis, the first reference here. So I think he was kind of the first to actually build up a proper formal model of what weak isolation levels actually mean. And then that's other related things to this are Berenson's critique of number 6 here. They kind of introduce snapshot isolation and have a bit of a formal model around it as well. And then Peter Baylis and his folks, which would be, I think it's the VLDB paper number 5. Those 3 papers are probably the most interesting in that regard. So a little thing that I did was a project I call Hermitage, or Hermitage, or however you want to pronounce it, which is on GitHub. It's just a small thing where I basically took these papers that build up a formal model of what the different isolation levels mean and turned it into the suite of tests that I then ran on 4 different databases, or 5, just to test like what kind of things would actually happen. And it's really interesting. You get this big matrix of different checkboxes saying like what kind of race conditions, what kind of anomalies can happen on which database under which isolation levels. And that work is just directly transcribing the formal model that they've set up into code.
Thank you.
Thank you. More questions?
Excellent.
Hi. I'm not really into this transactional stuff, but is this serializable snapshot isolation the idea behind STM, software transactional memory?
I don't know a whole lot about STM, so I'm not really the right person to comment there.
Okay.
So my understanding is that STM tends to be within a single process for multi-threaded communication, though I don't actually know how those things are implemented nowadays.
Well, this logs that detects changes, it seems kind of what it is.
Okay, yeah. Yeah, so there could well be overlaps there. Someone else would probably be much better placed to comment on it there.
Thanks.
Phil?
They tend to be MVCC.
Phil says they tend to be MVCC, so that would probably be similar to like Postgres's snapshot isolation type thing. Okay, thanks.
Any more questions?
Okay, is it time for lunch?
Okay, yeah.
Hooray, thank you for coming.